So in the last video, we covered an introduction to partial fractions, kind of the intuition behind partial fractions, and then an introduction to the first level, or what I called a level of partial fractions, which was how do we split up a very simple fraction that has in the denominator what we call distinct linear terms. So maybe we have a denominator that looks something like the following, right? Some linear terms. And then we said that it would separate into something like a over the first linear term plus b over the second linear term, like so. Well, we're going to just kick off this video with level 2, and we're going to say that level 2 has two requirements as well. So the first requirement is, as always, that the degree on the bottom is greater than the degree of the polynomial that's on the top. And then the second requirement is going to be that, well, not really a requirement, it's more of like something that we notice, but if we have repeating linear terms in the denominator, so repeating linear terms, actually, we'll just say even just repeating terms in the denominator, right? What do we do if that happens? And so, for example, so what if we have something like 3x squared plus x plus 2 all over, and let's say we have x plus 1 and then x minus 1, but we have this squared, something like this, okay? So, before, actually, the first thing we should do is make sure that this meets our requirements, and it does indeed, because we're going to get an x squared multiplied by x, which is going to give me x cubed in the denominator, and that satisfies that the degree of the bottom is larger than the degree of the thing on top. Basically just means that our denominator as a whole is larger than the thing on top, which is kind of what we're aiming for. And now you're going to notice that we have some repeating linear terms. Specifically, we have x minus 1 being multiplied by itself 2 times. And so, if we were doing partial fraction decomposition before, we would have said that this, we might have taken a try and saying, that this is a over x plus 1 would be our first term, and maybe we would have thrown in a b over x minus 1 for the second term. But the question is, what do I do about the fact that there's something squared here? Do I put something squared like so? What do we do? And it turns out that the answer is that for however many repetitions you have, we're just going to add on another term up until the point when we hit, in this particular case, x minus 1 squared. Now, this is a little bit strange, so let me just illustrate. If I had replaced this 2 with a 4, then there would be a plus c over x minus 1 squared. There would therefore be a d over x minus 1 cubed, and then an e over x minus 1 to the fourth, and then we would stop. Now, again, there's reasons for this. There are slight variations for doing, partial fraction decomposition for something like this, but this is the way that I'm going to kind of roll with for this particular problem. So level 2 actually isn't so bad. We have a way of dealing with it. Our setup changes just slightly in that the terms that involve this x minus 1 squared, this repeating part, kind of just get expanded until exhaustion right here. And then the process kind of begins all over again. So very similar to the last example, at this point, we're going to try and get the right side to have common denominators. And so we have to notice that for this first term, I only need to multiply it, or rather, we should identify what the common denominator is. And the common denominator between the three of these things is going to be x minus 1 squared times x plus 1. Right, that's going to be our common denominator. And so in doing so, we're going to get a times, we need to multiply this first one by x minus 1 squared, because we already have that x plus 1 in the denominator. So we'll have x plus 1 and then x minus 1 squared. The middle term, we're going to need to multiply it by the x plus 1 and another x minus 1. So b times x plus 1 and x minus 1, and that's going to get us to x plus 1 times x minus 1 squared. And then for the last one, we'll have c, and we just need to multiply this one by x plus 1 to achieve our goal of a common denominator of x plus 1 times x minus 1 squared. And so once we've achieved this, we notice again that our denominators match, right, finally. And so, if all of our denominators match, then it must be true that the numerator needs to equal on the other side as well, right? This is all one giant fraction now, and we need the numerators to be equivalent. So this implies that 3x squared plus x plus 2 is equal to a times x minus 1 squared plus b times x plus 1 times x minus 1 plus c times x plus 1. And again, at this point, there are two different ways we could try and do this problem. So maybe I'll split it up over here, and I'll put, pick x's over here, and I'll put the balanced coefficients method over here, okay? And sometimes we need to use both of them. That's why I'm kind of preparing to do both of them. Now this time, I'm just going to try to start with the balancing coefficients method. So again, I'm going to look at the left side and say, well, how many terms with x squared are there, right? How many are there on the left side? I'm going to say, well, there's 3 of them, right? There are 3x squareds over there, so I'm going to say 3. That's all that's there on the left side. So we look on the right side and we say, okay, how many are there on the right side? And we say, okay, well, if we do the multiplication, we are going to end up with an ax squared here if we were to FOIL out this x minus 1 squared bit. So there's at least a of them. Same reasoning here for the b. There's going to be times x times another x is going to guarantee us a plus b term, and that's it. So we're going to put a little circle around this equation. We may end up using it in the future. And we're just going to kind of keep going down the line. So how many x's are on the left side? There appears to be one of them. Right? There's just the one of them. How many x's on the right side? Now, this time you have to be a little bit careful because we have to do the actual algebra. So x minus 1 squared, if we were to FOIL that out, is going to be x squared minus 2x plus 1. So there's going to be a minus 2a of them because that a is going to distribute in, right? If we have an a in the front here, the a is going to distribute in and give us that there's minus 2a of these x terms right there. Similarly, with this one, we have to do the multiplication, but thankfully, x plus 1 times x minus 1 is just x squared minus 1. So there are no bx terms, but there is a cx term over here, so there's going to be a plus c. So I'm going to put a circle around this as well. And then last but not least, you may notice that I'm aiming this time for 3 equations because I have 3 variables that I need to figure out, and you can't solve for 3 unknowns unless you have 3 distinct equations. So now I'm going to ask the same thing. I'm going to balance the coefficients, and we're going to do the constants. I'm going to say, well, there's 2 on the left side. On the right side, there's going to be a from that first term. There's going to be a minus b from that second term, and then there's going to be a plus c from that third term there. Now, at this point, there's a couple things to notice. Number one, these problems are very closely related to each other, right? They all involve the a's and the b's and the c's. And moreover, if you were to have one of them, for instance, if I knew what A was, then I could figure out B, and if I knew what A was, I could figure out C, and then I would be done. So we're almost just waiting for one domino to fall. But there are a bunch of different ways to do this that you may remember from a pre-calculus 1 class or an algebra 2 class, which is you can do some substitution, right? You could take this last equation here and do something like we could say that A is equal to 2 plus B minus C by putting all that on the left side. And then I could take this stuff, I could jam it into here, right? And I could get that 1 is equal to negative 2 times 2 plus B minus C plus C. And this is going to get me a negative 4 minus 2B plus 2C plus C. So we get 3C here. And then what I could do from here, right, is I could solve for another one of these variables and so on and so forth. Excuse me. And I could keep just back substituting until we get, to some point where we could solve these equations. But at this point, I'm gonna pause, right? This is a method that we learn how to do in Algebra 2 class, so I'm not gonna go too deep into it right here. I'm just doing this as a bit of a reminder. But I'm gonna bounce on over to the pick some x values one. And again, I'm gonna say, if this yellow line that I have written here is true, right? If we actually have equality in this statement right here, then this has to be true for any value of x. And so if I was trying to evaluate it for some easy values of x, I would probably pick a value for x that's going to make a lot of stuff cancel out. So for instance, if we try to let x equals 1, then what's that going to do on the left side? So on the left side, that's going to give us 3 plus 1 is 4, plus 2 is 6. So we get that 6 is equal to, now if I plug in 1 here, it's going to cancel out. And if I plug in a 1 here, we're going to get cancellation because 1 minus 1 is 0. So I'm just immediately going to get that 6 is equal to 2c. That immediately gets me that c is equal to 3. And like I said, now if I know c is 3, I can solve for a. And if I know what a is, I can solve for b, right? You could stop at this point and we would be good to go. But just for the sake of just going, doing a little bit more practice, I might try and say, let's do one more, because picking x is equal to -1 is probably also a good choice. So x equals -1. Now, again, careful with your algebra, but we're going to get 3 here. Minus 1 is 2, plus 2 is 4. So I'm going to get 4 is equal to, if I plug in -1 here, I'm going to get -2 squared, which is 4. So I'm going to get 4a. The -1 is going to cancel out this middle term here, and the -1 is also going to cancel this term out. So I immediately get that a is equal to 1. And at this point, you'll notice that there aren't really any other nice x values to plug in per se. None that are going to cause everything to cancel out like immediately and give us some answers. But that's okay because, again, our goal now is to solve for b. And I have 2 equations that solve for 2 of the variables, so I only really need 1 more. You could pick any x value you like. I might try doing x is equal to 0, because on the left-hand side here, that's going to give me 2. And on the right-hand side, if I plug in 0, I'm going to get a here, because -1 squared is just 1. I'm going to have a -1 here if I plug in 0, so a minus b. And then if I plug in 0 here, I'm going to get a plus c, which you'll happen to notice is the same exact term that we get when we look for the constants. That's okay. But at this point, I know what a is, I know what c is, and we could very quickly figure out what b is. So this is the last time that I'm going to go through both of these methods, because the rest of the variants of how to do partial fractions, the levels, if you will, are just us, figuring out exactly how to get started. Right? The process for actually doing the partial fractions and solving for it is pretty much entirely the same. It's just, what do you do under different situations? So just as a reminder, level 1 was if we had distinct linear terms in the denominator. Level 2 is what happens if we have some repeating linear terms in the denominator, right? And now let's move on to level 3. So we'll say level 3, whoops, let's not use a highlighter. Level 3. Okay, so level 3 is going to be the same old, right? Step 1 is that the degree on bottom is larger than the degree on the top. But the second thing now is what happens if we have an unfactorable quadratic. And so what I mean by that is we need a non-factorable, or maybe what we might call irreducible quadratic term. Okay, and you might be wondering, where that little bit comes from. Let me give you an example. So if I were to give you something like x plus 1, and then I gave you x squared minus 1, this thing is a quadratic, but it's not irreducible. It's not factorable, because this is a difference of squares, and it actually does factor into x plus 1 and x minus 1, right? We know that we have the quadratic formula at hand. You can factor a lot of different quadratics into linear terms. So it turns out that most quadratics, every quadratic we can plug into the quadratic formula and figure out if we can actually turn it into linear terms or not. But an example of one that is irreducible, one that we can't do that, would be if I put a plus sign in between there. Because if you were to try and solve this, right, trying to factor it, x squared plus 1 equals 0 gives us x squared is equal to -1. And since we're not working with complex numbers, imaginary numbers, we don't have a way to factor this. You can quadratic formula it all you want, you're not going to be able to factor it. So when we talk about this irreducible quadratic. We're talking about a quadratic that does not factor. So now, we still have a linear term here, but the question is, how do I break this up, and how do I deal with the fact that I have an irreducible quadratic? So the first term is exactly what you would hope it to be. It'd be a over x plus 1. But the next one, you would think, okay, well, I can't do anything with this x squared plus 1, so it's probably just going to be x squared plus 1, and that'd be a really good intuition. But the strange part is what comes next in the top. And the thing that we have on the top is a bx plus c. So this one looks very different from the other decompositions we've done before. There's a reason why it's bx plus c. It's not like it comes out of left field, and it's actually a pretty simple explanation. But for the sake of this video and not causing a bunch of confusion, I'm going to say if you would like to know further why this looks like this particular format and not just something super nice and slick like this, it's a good question for the discussion or the emails. But yeah, so this is how we would break it down, and then everything from here on out follows this exact same process. We would still do a times x squared plus 1. I would need to multiply this bx plus c term times x plus 1 on its own. That's going to give us our common denominator of x plus 1 times x squared plus 1. And from here, we're going to balance out the numerators again. We're going to say this numerator has to equal this numerator, and you can go about doing any method you want for solving for your a, b, and c in this particular way. One thing you might notice, though, is that if we were doing integrals, right, integral dx, then when we split this up, integral dx, kind of depending on what we end up getting here, this integral could actually be really easy or still be a lot of work. We might get lucky with a u substitution. For instance, if this coefficient for b was 2 and then our constant was 0, then I would just have a very simple u substitution. It may be the case that I would have to take this and split it into bx over x squared plus 1 and then plus c over x squared plus 1. And again, this part you could do with a u substitution, because if u is equal to x squared plus 1, then du is just 2x dx, and we would be able to, to work with this bx term. But here at the end, we would have number over x squared plus 1, and there's no u substitution to be done. But hopefully, again, we're not too intimidated, because x squared plus 1 looks a lot like tangent squared plus 1, and we could start doing some trig substitution to figure this out. But this is why this is level 3. The big deal here is that we have this, what we call irreducible quadratic, a non-factorable quadratic, and so it gets this kind of funny little form. Level 4 is just this exact same thing on steroids. So level 4 is, I'm going to say just the same conditions, but repeating terms. So repeating irreducible quadratics. And those work in the same way that you would expect them to after having seen level 2. So if I had something like this, and I had like x plus 1, maybe just for the sake of example, x plus 1 squared times x squared plus 1 cubed times, just to make this one just absolutely bananas, and x cubed here, we very carefully would need to start doing some work with this. So we'd say, okay, this first one is going to deal with this x plus 1 squared, and x plus 1 is a linear term, but it is repeating, so we do have to we start at x plus 1 and we build our way up to x plus 1 squared. Now we're done with that term. Now here, we're going to start off with cx plus d over x squared plus 1, what we just learned from level 3. But you guessed it, we have to kind of keep going, ex plus f, and we have to write x squared plus 1 squared, and we got to do a third one, right? Gx plus h over x squared plus 1 cubed. Now we've satisfied that one as well. And then we have our last linear term here at the end, this x cubed, which is going to be, what letter comes next? I guess I over x plus j over x squared, ooh, gotta zoom out even more, plus k over x cubed. And yes, you would have to kind of go through this. You can imagine that if these problems get too hairy, this could take a really long time. But again, if we're just doing integrals, some of these integrals are really easy to solve, right? This first integral is really easy to solve. This one's a u substitution. This one you probably need to split up. This one might make me cry. This one might make me cry. But natural log, this is a power rule, that's a power rule. So there's some like give and take, which is a lot better than just having one ginormous impossible integral that we would just have to leave. I also do want to point out, I'm just putting the number 1 up here because I'm super lazy. This could be any sort of polynomial function as long as we still satisfy the condition that the degree on the bottom is greater than the degree on the top. So those are like the big ones. And now we kind of reach level 4.5. And so this one will change color. We'll do it in red. Level 4.5. And so this one, we've really kind of exhausted everything in terms of what do we do with the different denominators. This one is what happens when the degree of the denominator is equal to or less than the degree on top. So basically what happens if you have something like x cubed minus x plus 4, and on the bottom you only have a term like x squared plus x plus 2 or something, right? You have something like this where the thing on the top is larger than the thing on the bottom. And they could match, right? Their degrees could match. So even if I had something like a 2 here, what would we do? And the answer is, just like we learned about when we were kids, if we had 10 over 4, the way we used to deal with this, if our goal was to turn this into, something with more usably bite-sized fractions, we'd say, well, 4 goes into 10 2 times, leaves us with the remainder of 2, and we would say that this is the same thing as the fraction 2 2/4, right? Whenever the thing on the top is bigger than the thing on the bottom, that means we can actually do division and we could get something like this. And we're going to use that same idea over here to deal with this rational function, which is that because we have a rational function whose numerator is quote unquote larger than the denominator, we're going to first do long division. So we're going to first do long division of polynomials, okay? Now, if you have never seen this before, I'm going to try and give a small crash course, but hopefully you've all seen this in some way, shape, or form. So let me remind you how long division works with numbers. If I were to give you how many times does 3 go into, let's say, 911, all right? The first thing that we do is we say, okay, how many times does 3 go into 9? And we say, okay, it goes in 3 times. We do some multiplication here. We write down the number 9. We do subtraction, and we say, what do we get left over? There's a 0. Cool. We bring down the next term, 1. We say, okay, how many times does 3 go into 1? We say it goes in 0 times. And we'd say, okay, you're going to do multiplication. That's going to leave us with 0. We do subtraction. Great. We get 1. And let's use a different color, 1, and then we get to bring down this next one. We say, okay, how many times does 3 go into 11? We're going to get 3. We do multiplication one more time. We get 9, subtract, and then we're left over with this number 2, and because 3 doesn't go into 2 anymore, we could just say that our final answer is that, 911 divided by 3 is equal to 303. And then, what do we do with that remainder? It becomes the fraction 2/3, right? We can't divide the 3 into the 2, so we just leave it as is. And that's what we would say that this becomes. And so this works the exact same way for polynomials. So if I were to do this polynomial long division, I'm going to put x squared plus x plus 2 right there. And then on the right-hand side here, we're going to put the x cubed minus x plus 4. All right, now, the thing that's a slight bit different is that there's a lot of stuff here on the left that we're trying to divide into a lot of stuff here on the right. And the way the polynomial division works is we say, look, out of all of these terms, okay, the x squared is always going to be the largest term. So that's going to be the term that has the most amount of trouble fitting into any one of these terms over here. So when we do long division, even though there's this whole thing that we have to look at, we're only going to focus on the biggest term, this leading term. And so the first question that we're going to do is we're going to look at that one and this first term, just like we did over here, where we looked at 3 and we asked how many times does it go into 9. We're just going to, ask ourselves, how many times does x squared fit in to x cubed? Now, that may be kind of a strange question to ask. So instead of writing it like that, I'm going to say, how many times does x squared fit in to x cubed? I'm going to write it like this. And all of a sudden, the answer kind of becomes pretty straightforward. X cubed over x squared just simplifies to x. So x squared goes into x cubed x times. We're going to go through here. We're going to do our multiplication. We're going to get x cubed. We subtract. We get 0, and we say, great. And we pull down the rest of this, right? We have a minus x plus 4. Now, you could pull down just one term if you'd like minus x. And you're going to notice that x squared, in this particular case, will not fit into x, right? We're going to get how many times does x squared fit into negative x? And the answer is it doesn't, right? Like, you could reduce this to this, but still this is not going to fit into the top. And so this is kind of the part that kind of reminds us of the remainder from the previous problem that we just did here, which is when this number 3 could no longer fit in to what we had left, we just wrote that off as a remainder. And so that's what we're going to do here. We're going to say, okay, so x squared doesn't fit into minus x. It's definitely not going to fit into minus x plus 4. So we were going to say that we have kind of a remainder of negative x plus 4, if you will. And all that means is that this fraction, x cubed minus x plus 4, divided by x squared plus x plus 2, is going to equal x, because that's what we got. That's the only thing we were able to get out of this. And then notice, right, if you have a remainder, 303 2/3, by the way, in case you forgot, is the same thing as 303 plus 2/3. And so on the right-hand side here, I'm just going to write this is equal to x plus negative x plus 4 over x squared plus x plus 2, right? And now we're cooking again, because this is going to fit one of the other criterias, right? Hopefully we can factor the denominator into some linear terms, and that we can make some progress with some partial fractions on this piece. But again, if we were going to just be integrating this thing here on the left, dx, now we're just integrating this thing dx, and at the very least, I have a head start right here, right? The antiderivative of x is just x squared over 2. Now I just need to deal with, how do I integrate the remainder portion? And you can use any technique that you've learned in the class so far. Typically, partial fractions tends to still be kind of what you need, depending on how difficult or easy the problem is. But yeah, I mean, that's it. That's as crazy as this gets. So if you feel like you need some more review on how to do polynomial long division, maybe you never saw it in pre-calculus 1, or it's just really rusty, I'd say you can shoot me an email, post it in the discussion, or check out any sort of online resource. If you just Google long division, polynomial long division, there's going to be a ton of worked out problems on how to do them. This version doesn't happen a ton, but it does happen. So if it shows up on the homework, you're going to need to be able to do that long division. But yeah, the craziest, the hairiest ones you might get are going to be ones where you have a bunch of repeating terms in them, some irreducible quadratics. Sometimes, you're going to get one that looks like x squared plus x plus 2, and you're going to have to figure out, does this thing even factor? You're going to have to put in the work and do the quadratic formula or something and be like, yes, it factors, or no, it doesn't factor, because, depending on if it splits into, x plus something and x plus something, or whether it doesn't, is going to really impact, what those partial fractions end up looking like when you go to try and complete this integral. So that's going to do it for this video. It's just covering the other levels 2, 3, 4, and what I call 4.5. If you have any questions, feel free to ask. Hopefully it's not too bad. And then when you're ready, let's head to the next one.